So here's an example of curve sketching, again from chapter 5 in your text. And here's an example we're going to go through. It says discuss the curve, and we talked about what discuss means. That just means tell me all about it, right, in a mathematical sense. Here's the curve, so here's the graph. And here are the sections A to H. So, of course, it really means sketch the curve, noting every characteristic, that we've talked about. And so they just say discuss the curve under the headings A through H, which we just discussed. All right, so A was domain, right? Okay, so what do we know about the domain of this function right here? Are there any restrictions? So any values for x that would cause a problem mathematically, anything that would make a negative number under a square root. Well, don't see any square roots there, or fourth roots or sixth roots. So that's no problem. Do we see any denominators, any rationals here? No. So this is a straight polynomial function. There's no restrictions. X can be anything. So the domain is XER. That's all I will require of you to say. There's no restrictions, so there you go. Done. Got it? B. B talks about what? Intercepts. Okay? Intercepts. Now, let's find which one you want to find first? Y-intercept? This one's easy to find. There should only be one y-intercept if it's a function, right? This is a function. It's continuous because there's no restrictions. There should be one y-intercept somewhere. So we say 3 times 0 to the 5 minus 5 times 0 cubed. So if we evaluate that, that's 0 minus 0. Y equals 0. So the y-intercept is 0, 0. Or you could just say y equals 0. Okay, well, because this is the origin, it's also what? It's a y-intercept, but it's also... Oh, no, we're not at symmetry yet. But it's also an x-intercept, yes. Is it the only one? Maybe. But could there be others? X-intercepts? Yes, but we know that, hey, we've got one y-intercept here as well. Do you see that? Yeah? See that? Does everyone understand that? If your y-intercept is the origin, that's also an x-intercept. Okay, just wanted to note that. All right. So what about x-intercept then? Let's let y equals 0. And we've got 3, what was it, x to the 5th minus 5, x cubed. Okay. So can we factor this to make our lives a little bit easier? Yeah, we can. We can take an x cubed out. 3x squared minus 5. Okay. Now, we've got two factors here. Obviously, x cubed equals 0 at x equals what? 0. Okay, we know that already. Thank you. We've got that already. And what about this? 3x squared minus 5. Where does that equal 0? Because, again, where either of the factors equals 0, that's where we have this product being 0. So, okay, we've got 3x squared equals 5. Now, here's the thing. If this was a negative 5 right here, if that happened to be a negative 5, you can't take the square root of a negative number, so there's no x-intercept responsible there, or represented there. That's not the case. So we'll keep going. Can we solve for x here? Sure can. X squared equals 5/3. X equals plus or minus, make sure that you do plus or minus, okay, when you take the square root of something, root 5 over 3. And for now, I'll just let you leave it as root 5 over 3. So, we have y-intercept 0, 0. X-intercepts are at x equals 0 and x equals negative root 5 over 3 and positive root 5 over 3. And of course, as points, these are 0, 0, negative root 5 over 3 comma 0, and positive root 5 over 3 comma 0, because the intercepts, the y value is 0, right? Now, I'm trying to get all of this on one screen at one time for you, so it's a bit messy. You would try try and write this out so it's a bit neater, but at least please highlight your intercepts, okay? And let me know what you've uncovered here. Okay, questions, or is this good? Getting this? All right, C, what's C? Symmetry is C. So, as I mentioned before in the lesson, you might want to check these two, f of 1 and negative 1. If you do that, then you can examine the answer that you get, and you have an indication if there exists any symmetry. So f to the negative 1 is going to be, let me get back to my, is what? Negative 1, oh, where are we? Oh yeah, there it is. 3x to the 5th. Okay, sorry. 3 times negative 1 to the power of 5 minus 5 times negative 1 to the power of 3. So if we evaluate that, that's negative 3 plus 5, right? So that's negative. So that's 2. And f to the positive 1 is going to be 3 minus 5. It's going to be negative 2. Okay, does that look right there? So what does that tell us? That tells us that if you look at this here, f to the negative 1 is positive 2, and f to the positive 1 is negative 2. So does that follow, if we go back to the notes there, does that follow either one of these, odd or even? Does it look like that, or does it look like this? Or neither? Okay, so if one is, basically one is positive and one is negative, right? So f to the negative 1 is 2, f to the positive 1 is negative 2. Same number, but different sign. So that appears to be an odd function. Okay, so positive 2 and negative 2. If you have the same number but different signs, odd. If you have the exact same number and the exact same sign, it's even. Anything else, no symmetry. So this is symmetry about the what? Symmetry about the, very good. Symmetry about the origin. Okay, let's stop right now just to see, let's stop so far to see what we have. So we have, what do we have? No restrictions on the domain, so no asymptotes that we know of, no verticals, right? What was the next one? Okay, where are the intercepts? What values again? What values for the intercepts? 0 and negative root 5 over 3 and positive root 5 over 3. Alright? So we know we have this so far. And we know we have symmetry about the origin. So we don't know where this graph is going, up or down, but we know that there's some kind of symmetry about the origin. So it's going to be rotated about the origin. Alright, so I just heard the bell ring, so that's the end of our class. What I'm going to get you guys to do for your homework is to finish this out. So D through H, finish it out, and then we'll come back tomorrow. We'll give you a fresh set of questions to work on here in class, okay? Alright, so as we continue this question here, the asymptotes. What we've noted is that there's no restrictions on the variable. So that gives us an indication that we probably don't have any vertical asymptotes at all. And horizontal asymptotes, if we took the limit of the function as x approaches infinity, even if you just look at this right here, you know, as x gets larger, is there a value that this expression seems to approach? And the answer is no. A regular polynomial would not have a limit as x approaches infinity because it would just get larger and larger and larger without bound. So for asymptotes, it's a polynomial function, and there are none. So no asymptotes. Okay? And you can use your reasoning for that, but if you mention something like it's a polynomial function, as x approaches infinity, you know, the value of the function increases without any bound, you know, stuff like that. If you just kind of explain yourself there, but you know, just to show that you've thought about it. E. E is intervals of increase or decrease. Okay, so now is where we need to start taking the derivative of the function here, right? So we look at this function right here, 3x to the fifth minus 5x cubed, and we'll take the derivative there. So let me write this heading down here. Increase and decrease. So the derivative is 15x to the fourth minus 15x squared, and if we factor that, we get 15x squared times x squared minus 1. And this is, of course, the difference of squares, so really you could write this as 15x squared times x minus 1 times x plus 1. Now, intervals of increase and decrease, we're going to want to apply, or we're going to want to use sign analysis here to find out where those intervals might be. And so we put the factors up here on the left, and we do some sign analysis. We're going to determine what is happening to our derivative down here. And so 15x squared is 0 at 0, right? This is squared, so any negative value for x is still going to be positive here. So it's positive on either side of the 0. The critical number here, again, we're identifying critical numbers here as well with our factors. We have a positive 1 right here. It's negative ahead of that, and positive values for this factor after 1. And we have negative 1 here. There's a critical number here. That makes this factor 0. Negative here, positive over here. So the derivative is positive in this interval. It's 0 at negative 1. Again, that's our critical number. That's the C value. This is positive times positive, so that's a negative there. 0 here, negative here as well. 0 here, and positive here. Okay? So this is what our first derivative looks like, and these are also critical numbers. So intervals of increase, it's increasing on what are the intervals? Well, wherever there's a positive, it's increasing. So we're increasing on the interval negative infinity to negative 1, and also 1 to positive infinity. We're decreasing wherever the first derivative is negative. So here and here, and negative 1 to 0. Typically, we don't include this 0. We'll state two separate intervals because there is a disruption in this negative sign here. So let's do this interval and this interval. So that's negative 1 to 0 and 0 to positive 1. So there's your intervals of increase and decrease. We see that the function, because of this, we see that the function will rise in this area. It'll get larger, and then it'll decrease, and it'll get larger and decrease. Decrease and my bad. That's backwards. It'll decrease again over here, and then it'll start to increase in this interval. So you kind of get to see now where the function begins to rise and fall. That's what E is telling us, the heading E, intervals of increase and decrease. All right, moving along to section F. In this example, that's the max and min values. And we can just take a look at our sign analysis to look at where max and min values might be. And of course, like we learned early on in the chapter, and last chapter as well, that where the sign for the first derivative, where that changes from positive, right, through 0 to negative, we are going to have a local maximum here. And so where does that happen? Positive through 0 to negative. It happens right here at negative 1. So we have a local max value at x equals negative 1. So that's where we'll start. Do we have another max value or a minimum value to speak of here? Well, if we take a look at some more things here, we have negative derivative here, 0, negative. That's interesting. Negative derivative, 0, and negative again. Does that represent a max or a min? Or neither? Right, it's neither. So it's neither a max nor a min here at 0. So we're not going to mention that one. But over here we do have a negative through 0 to positive. So the direction, the sign changes, and of course that yields, that's a local minimum. So we have a minimum at x equals positive 1. You do need to write these as points, so yeah, again, what you need to do is you need to throw negative 1 and positive 1 into your original equation, which actually we did for symmetry, didn't we? Yeah, look at that. So the points are negative 1, 2, and 1, negative 2. Negative 1, 2, and 1, negative 2. So there's our local max right here, and our local min right here. All right. Now we could, if we want to, start adding to our diagram. So why don't we just take a minute and do that? I'm just going to grab this and bring it down here. I could recreate it, but I'll use the technology we got. Oh, that's nice. The y-axis. Where to go? Well, just make the y-axis. So negative 1, 2. Okay. Oh, negative root 5 over 3. Is that, where's 1? Is it 1 over here or 1 over here? Well, if you don't know that, you can jump on your calculator if you really want to. You know, or you just use your intuition here to figure it out. So this is 5 over 3. It's 1 2/3, and the square root of that, is that going to be, you know, greater than 1 or less than 1? So negative 1 is about here, and positive 1 is about here, and the max value is negative 1, 2. So we can start to piece this together. The min value is 1, negative 2, about there. So what you can kind of see is we're going to have, you know, some kind of, it's going to go up here to a max, it's going to come back down here to a min, back up here to our intercept. And so we're kind of seeing right now what's happening. Now, in between here, we don't have enough information to draw this with certainty. So that's why we got to keep going. We got to keep going to find out what's happening in this region and maybe this region. Because maybe something's happening. We don't know the concavity yet. You know, we don't know what's happening there. So that's why we need to keep going. We could assume that it looks just like this. And we might be right, and we might be wrong. So that leads us to the next section here. Oh, wait, did we do F? Did I jump ahead? Yeah, max min. All right, so G is concavity. And so that involves the second derivative. So we need to find out what the second derivative is. And that's the derivative of the derivative. And so the second derivative is 60x cubed minus 30x minus 30x. Factor that is 30x times 2x squared minus 1. Alright, so what this tells us, when we set this equal to 0, is where are our points of inflection. So the x values that yield 0 here for the second derivative are our points of inflection. So at x equals 0, from this factor, we're going to get a point of inflection. And we're also going to get a point of inflection where? Well, where this other factor equals 0. So that's 2x squared equals 1, x squared equals 1/2, x equals plus or minus the square root of 1/2, or 1 over root 2, or if you're simplifying, root 2 over 2. Okay? So those are the values here that we will use for our points of inflection points. Well, that's interesting, isn't it? Because we just talked about the fact that we don't know what's happening in between here, and it just so happens that we have, you know, a point of inflection right about here and right about here. Interesting. Interesting. So the concavity changes. Well, let's do a little sign analysis here to find out exactly what concavity we have. And so the sign analysis is set up like this. So we have a 0 at 0. And this one here, of course, we have zeros at plus or minus root 1/2. So negative root 1/2 and positive root 1/2. We have zeros here, don't we? Now, what happens to the signs in between here? That's important. You can use a test point if you want, like 0. What happens if I put 0 in? Well, 2 times 0 squared is 0 minus 1. It's going to be negative in there. And it's going to be positive here and positive here. So what that tells us is this. We have negative concavity here. Comes to a 0 here, and this is positive 0, negative 0, positive. Alright? And so that changes things in our graph alright, doesn't it? Alright, so I'm going to just recreate this graph, what we have so far here, down below. Alright, I want to just show you what I did down here with the x values for the points of inflection. To name the points of inflection, you do have to find out what the y values are. So, a little bit of math here. This is the exact value right here of the y value for the point of inflection for x equals negative root 1/2. This is the decimal value. So if you're just graphing it right here, the decimal value is usually okay. So here's the point of inflection up here, and another point of inflection here. So if we're trying to figure out how this graph goes, we have to think about our concavity. Our concavity is concave down from infinity, negative infinity, through the intercept to the maximum point, also down to the point of inflection. So this is a kind of a concave down section here, all the way here. Okay, here or there. Now the concavity changes, doesn't it? Because if we go back to our sign analysis here, negative, point of inflection, positive now. So that is concave up. So from here we have to try and draw just a section of the graph where the concavity is concave up. See that? It flips to down, and so we can continue on like this with a down. This is a point of inflection, so that means the concavity changes to positive. And then it's still positive after here, so it kind of looks like this. And what I've tried to show you is that we do have symmetry as well about the origin. Remember, it's an odd function, so it's symmetrical about the origin. And dotted lines, solid lines, you probably should do a solid line, so if you carefully go over that with a solid line again and try and make it look as good as you can. That is your graph. If you want to confirm that with a graphing calculator, you certainly can, but that's what it looks like, and that's what you should have gotten for this example, where we are plotting this graph using calculus methods without a graphing calculator or technology. So that's your example there, headings A through H, and of course sketching it would be, that's heading H here actually, is the sketch, right? So just putting it all together. So there's your example, and that's all the way worked through. Yeah, it's a long question, but if you can do this question, you're well on your way to understanding and being able to do what you need to do for Chapter 5 here.